Greetings and welcome to a conversation with the UT Dallas Associate Dean for Undergraduate Studies, Professor in the School of Natural Sciences and Mathematics, and Space Scientist at the William B. Hansen Center for Space Sciences, Dr. John Hoffman. Dr. Hoffman's instruments have helped unpack the mysteries of our solar system, from 3 Apollo missions to the Moon to test atmospheric conditions, to the Pioneer mission to Venus in 1978, and the landmark Phoenix mission to Mars in 2008. His spectrometer helped explore Halley's Comet in 1986, and he has had past experiments revolve around the Earth on a handful of orbiting satellites. The recent Phoenix-Mars mission, where the presence of water was definitively determined, depended heavily on a system of small furnaces and a mass spectrometer system he designed and built. He came to the Graduate Research Center of the Southwest in 1966. In 1967, the Research Center changed its name to the Southwest Center for Advanced Studies, later becoming UT Dallas in 1969. Dr. Hoffman has served all 3 organizations with distinction, and I'm honored to visit with him today. Thanks for being here, Dr. Hoffman.
You're quite welcome. I'm happy to be part of this program.
A bachelor's degree from St. Mary's College in Minnesota, a PhD from the University of Minnesota. How is it you came to Texas in 1966?
Well, I came to Texas via Washington, D.C., actually. I kind of came from the north to the south in 2 steps, you might say. I was invited to work at the U.S. Naval Research Laboratory in 1959 and joined the Space Science Group there, which was headed by Dr. Herbert Friedman. This group was one of the pioneer organizations in studying the atmosphere of the Earth. And actually, it was a group formed before actually NASA was formed. NASA was formed, basically the atmospheric part of it, out of the group at the Naval Research Lab. I was given a job opportunity there, which I took and was very happy to do that. We started working there on in the group called the Aeronomy Group under a fellow by the name of Charlie Johnson. We were working with what are called Aerobee 150 rockets that were flown at the White Sands Missile Range out in New Mexico. And these would go up to about 150 kilometers altitude and take different scientific instruments that we were developing there at NRL. These flights were, of course, suborbital. They just went up and down about 10 or 15 minutes duration. Well, we started to learn a lot about the lower atmosphere of the Earth. At that point, I took the mass spectrometer that I was working with at the University of Minnesota on my doctoral dissertation, which was, of course, a room full of equipment, and miniaturized it down to a little box that was about a foot cubed and weighed maybe 20 pounds or something like that, instead of hundreds of pounds, and great big operation that I was typically using at the University of Minnesota. We flew these rockets at White Sands, and we're studying the lower ionosphere, that is the electrically charged particles of the Earth, up to altitudes of about 150 kilometers.
What did you know at the time? Was anything space science related emerging out of Dallas? I mean, how did you become aware that a program might even exist for you and an opportunity here in Dallas?
I had a number of successful flights and had published some data and some information about it. And we'd also had a rocket that went up to 1,000 kilometers, which was called a Javelin rocket. And after that, there was a meeting of some organization in Washington, as of course there are many such organizations that meet in Washington, D.C. area. And several people from the Dallas group had come to Washington, and I had attended this meeting. And I really hadn't known these people, although I had known of them. And Bill Hansen particularly and Walter Hakela are 2 that contacted me. And I guess we had lunch or something like that. And out of that conversation, they said, well, why don't you just come down to Dallas and give us a seminar? And told me a little bit about the Graduate Research Center of the Southwest and what the goals of the organization were and how it was formed and so forth. I said, well, sure, why not? I'd be glad to come down and present a seminar down here. And so I did. And that kind of led to more discussion and eventually an offer of a position here. And so actually my wife and I came down and kind of checked out the area, and we kind of liked what we saw. And so we actually put in an offer on a house right off the bat. This was bought in September of of 1966. And I had received then an offer of employment here at the Graduate Research Center of the Southwest. And so we decided, well, we'd accept it and come down here and try it out for 5 years. Well, I think since this is 2009, that 5 years is not quite up, but it's getting close to being up. But anyway, we did move down here. The house was completed in November. We moved in November of 66, and we had 3 children at the time. They were all very young. The oldest was 5. And so we thought, well, this might be a pretty good place to raise the kids. And I liked the atmosphere at the Graduate Research Center, and certainly Bill Hansen and Frank Johnson were very well known in the field. And I thought, hey, this is a great opportunity, and I could join them. And so I came. And I'm very happy I did.
Were you sort of on board from the beginning about performing space science research in North Texas?
I think that, looking back on it, that actually it seemed like a very good opportunity. It was a new organization, fairly new. It was only a few years old at that time. And, of course, Bill Hansen and Frank Johnson had developed, an excellent reputation, along with Walter Hakela and several others, that I decided that, this would be a great opportunity to actually, further my career in studying the atmospheres of the Earth and hopefully eventually the planets. I wasn't into that yet, but that developed later on. And so I thought it was a good opportunity and decided, hey, let's try it.
And what did campus look like at the time? What did you see when you were brought here for the first time?
Well, it was a big open expanse of land and one building right in the middle of it, known as the Founders Building, because it was built by the 3 founders, Johnson, McDermott, and Green. And what's now the Founders Annex was the power plant for the Founders Building, and that was it. And, of course, we could drive right up to the front door and park. We didn't have to walk for blocks away, and so... but the rest of it was cotton fields. And basically our house was just south of Arapahoe Road, just west of Coit. That's where we, bought this house. And north of Arapahoe was all cotton fields. So things have changed.
Who were some of your early contemporaries on campus? Who were the people that you got to know and you affiliated with, and they helped you get acclimated to life at that time in the one building that existed on campus there in Founders?
When I first came, I was assigned a laboratory space and given an office on the lower floor of the Founders Building. Well, of course, that's where the space science area was. And Larry Brooks was assigned to work with me. And Larry worked with me the full time up until he retired just a few years ago. And he was kind of a jack of all trades in the lab, an excellent worker. He could do almost anything. He was a technician, but he got very adept at vacuum technology and vacuum systems. He could find a leak anywhere that nobody else could find in a vacuum system, which is, of course, quite critical. And so he was one of the people that worked with me. And then, of course, I worked with the group. I worked with Hansen and Walter Hakela, and Brian Tinsley was along at that time. And they were all part of this space science group here under Frank Johnson. He was the leader of the group. And, of course, then he became the first president of the university. He was actually interim president for several years when the university was first formed out of the Southwest Center for Advanced Studies. I mean, just a whole bunch of people that it seemed like when a person came, they stayed almost forever because there was very little turnover. I think the work conditions were so good that people just liked it here. And so it was a pretty close-knit group. And by the way, we had the best cafeteria in the world. It was on the upper floor in the west end of the building.
You're not the first person that I've heard say that. That the food was remarkable, and 40 some odd years later, it's still that memorable.
Oh yeah. I mean, you can't forget that. It was so good.
How did you first become involved in the Apollo missions?
The Apollo missions, of course, they started with Apollo 11, which is this summer is going to be the 40th anniversary of the flight of Apollo 11 in 69. There was plans for, all these different missions coming up after 11. There was an opportunity to look at the atmosphere of the moon. And, of course, the first thing you might think about the moon is it doesn't have an atmosphere. So we were going out there to try to measure nothing. But the point is there is, a layer of gases around the moon. It's just very, very, very rarefied. And so these opportunities came along, and in those days, NASA was developing, and there was a lot of funding. Opportunities came along. There were great abundance of opportunities, and it was kind of the golden age of space exploration. And so I wrote proposals and put them in for these missions, and I was fortunate enough to get contracts for them. We flew in the orbiter part of the missions on Apollos 15 and 16. And thought, and of course we found out later that we could not do this, that we could actually measure this rarefied atmosphere from orbit around the moon. And we were at 100-kilometer altitude, and, what we were measuring, we did measure some gases, but we figured out later on that they actually had come from the spacecraft and were gas molecules in orbit around the moon, and they were not really lunar atmospheric particles. But then we got down on the surface on Apollo 17 and actually made direct measurements of the gases in the lunar atmosphere and found out that the pressures, or the number densities, are basically less than what our best vacuum systems on Earth can produce, at least in those days. I think you can get down that level now, but back in those days in 1972. So it's a very, very, very rarefied atmosphere. But we were able to detect hydrogen, and we were able to detect put some limits on things like carbon monoxide and carbon dioxide.
Did anyone ever visit with you in the early days of your researching here and say, space science and Dallas, the two just don't seem to go together?
Well, I think that Dallas was coming of age, you might say, but it wasn't just my work, because both Hansen and Johnson were very well known in the field. And in fact, because of the work that Frank Johnson did, we were known as a center of excellence for NASA, and there were only several of those around the country. And so, and that's another thing that made it a great place to work at. Dallas was getting known in that field, but it's a fairly narrow field. Studies of the atmospheres of planets is a fairly narrow field, but it was getting known all over the world. That we were here in Dallas, and I don't know about, of course, this whole center here that was developing. We had excellent people in relativity. We had this whole group in molecular biology, and we had the geoscience group that was headed by Anton Hales that came from South Africa. So, I mean, this was getting to be quite a, well-known scientific endeavor here in Dallas. And but it was a team effort. There were a lot of people involved. I just was one, little cog in the wheel or whatever.
And did you ever think you'd be I know you mentioned earlier 5 years. I guess you never assumed you'd be working and researching at the same place 43 years later.
No, I mean, I don't think anybody can project that far ahead.
Right.
But, my dad was at the same school for over 40 years. He was a professor at St. Mary's College in Winona, Minnesota for, I think it was like 42 years, just about the same amount of time I've been here at UT Dallas. So, and that he did fine there. And so there was no reason, if everything was working fine, there was no reason to, move around. Mm-hmm. And it was a great place to raise a family. And so we just stuck it here,
We're visiting with space scientist John Hoffman from the William B. Hansen Center for Space Sciences at the University of Texas at Dallas. How did you become involved in the Phoenix mission and the eventual discovery of water on Mars?
The Phoenix mission is a special type of mission that was the first in a series of what NASA called scout missions. Well, the scout missions came along with a little different concept. They set up, then these were going to be much smaller missions. They were going to be dollar-capped missions, whereas prior to that, NASA didn't ever dollar-cap a mission. They always exceeded budget and so forth. But in the early days, there was plenty of money. It wasn't a real problem. But these scout missions were set up as principal investigator missions. In other words, they were saying, okay, we're going to fly to Mars. Now, each scientist who wants to do this, form a team, develop your science goals, your objectives and all that, collect the number of experiments that you need, the number of instruments you need to satisfy your science goals, contact the people that you want to put on your team, and then propose the whole ball of wax. And then the person who did this, who was in charge of all this, was known as the principal investigator for this mission. And all the people that supplied instruments were co-investigators under the direction of the principal investigator. And so it was a little different way of managing the thing. And then the dollar cap on it, which included the rocket that, to get there and all the launch costs and all that. And it started out at $375 million, whereas typically a Mars mission costs about 3 times that much. So it was a small mission. The weight restrictions were quite severe and so on. So a group formed at the University of Arizona. Peter Smith was the head of this group. I did not know Peter Smith. I hadn't met him before. But he'd been involved in Martian explorations for a number of years before that. So he was the principal investigator, and then several other scientists at the University of Arizona, namely Bill Boynton, who is one of the people that's in the group there. And I had met Bill before and had some interactions with him earlier on. And he called me one day and said, would you like to join our group and supply the mass spectrometer? We're going to do this experiment to look for surface materials. We're going to have a scoop on this thing. We're going to dig trenches, and we're going to, get samples. We're going to cook them in little ovens that we're developing here at the University of Arizona. And we need an analysis instrument that can look at all the gases that will be evolved as you cook a sample and decompose the minerals and, see what comes off, and do, mineral identification this way. So I became a co-investigator on this one instrument known as TIGA, Thermal Evolved Gas Analyzer. There were then 6 instruments planned for this particular mission. And they came up with this name, Phoenix, for the mission, and that was done, I think, by Peter Smith and others out there in Arizona. And the reason for that name, actually, it has a little bit of history, because in the late 90s, there were 2 missions flown to Mars that somehow didn't quite make it to the surface in one piece, particularly the Mars, what was it called? The Mars... Oh, gosh. Well, I'll come back to that name. But it crashed in the northern region, and a Mars Polar Lander, I think it was called. And it crashed in the northern part of Mars, and it was going to do very much what the Phoenix mission was going to do, but with a little simpler instrumentation. They did not have a mass spectrometer. They had a couple of other detectors that, again, they already had developed these little ovens. And so by the time that flew, of course, it takes about 5 years to put together one of these missions. So they had already built a spacecraft identical to the one that crashed in 99 to be launched in 2001 Opportunity. Mars and Earth line up in such a way once every 26 months so that you can launch off of Earth and get to Mars orbit and find Mars right there. So you have about a 3-week window every 26 months that you can launch to Mars. And so the 2001 launch opportunity was canceled because of the fact that the 99 spacecraft had crashed, and they didn't know exactly why, and so they had to do a lot of analysis and try to figure out. So that spacecraft then was just put in storage at Lockheed Martin, and it's called bonded storage. It's just it's in a temperature-controlled room and so forth. So on this mission then for Phoenix, I wasn't involved in that part of it, but Peter Smith and the engineers involved there, they looked at this spacecraft, and by that time they had done a sufficient analysis on it to know exactly what had gone wrong, and were able to easily correct the problem. It was a radar problem that cut the retro rockets off too soon, and it just crashed into the surface. So they'd done a very detailed analysis of this spacecraft, and they knew everything about it. So why not use the one that's in the stores and propose, putting different instruments on board and fly it? And so they did. And so basically, Phoenix then was rising out of the ashes of the crashed spacecraft of 99. So that's how they chose the name. It has nothing to do with Phoenix, Arizona, because the university is in Tucson.
Now, when you're getting involved in this particular project, do you think this might be the experiment that you could be involved in that discovers water on Mars? Do you have that degree of hope getting involved early on?
One of the goals of the Phoenix mission was to discover water on the surface of Mars. That was a prime goal to actually, there was a lot of evidence that water had existed on Mars. There were valleys and there were, formations, geological formations, materials that have been formed and so on that indicated that water had existed. But nobody actually found the water. It was just evidence that water it needed to have water to form these things. Like there were gullies and erosion and things like that. That could, at least as far as Earth is concerned, could only be caused by running water. And so, but the point is, water had not actually been identified. So that was one of the goals of the Phoenix mission, was really identify the water. And we did accomplish that, too.
The Martian day is 40 minutes longer than an Earth day.
That's correct, right.
So you ended up ultimately, during your time on the project, on the experiment, the active part of it, really, eventually, your schedule worked you around the clock.
Exactly.
What was that like, going to work in the middle of the night?
It was kind of interesting. Actually, I survived it very well, and I think most people did. Your circadian rhythms, if you travel to Europe and you got a 6-hour time change, once, then you get adapted to that time change, and you recover from it, and usually the adrenaline flows, and you are fine, and then I know I found it. Then I'm great there, and then when I come back home, then you crash for a while but this is a continuous change. It's 40 minutes every day. It doesn't sound like much, but in 10 days it's 400 minutes. That's many hours, and so it did. You walked through the night. You might be going to work at 8 o'clock in one day in the morning, and then a couple of weeks later you're going to work at 8 o'clock at night and working half the night, and then you're going to work at 2 o'clock in the morning and all that. And so fortunately, the rooms we worked in had 0 windows, and so you didn't know what was going on outside. We just lived there, and we lived on Mars time, and we didn't know whether the sun was shining or not. And I think that was a good thing. But we had to work on Mars time because there was no real-time activities. We had to send commands up to Mars. The transit time for a radio signal from Earth to Mars, because it was nearly on the other side of the sun, was 20 minutes one way. And then by the time it received the signal and then turned around, and if it sent the signal back within milliseconds, something like that, it was still a 40-minute time to go one way and then come back the other way.
In talking with you in the past, you've said that the early days of this mission presented some challenges, and that Mars was not quick to give up its secret about water.
It actually took us maybe a couple months before we actually got the water confirmed. Well, first of all, there were 8 ovens, and each of the ovens had a set of like French doors that they're open, because the ovens had to be sealed, or the entrances to the oven had to be sealed. And they were actually sealed with a separate cover here on Earth, so that we wouldn't get any materials in these ovens that we brought from Earth, particularly any kind of hydrocarbons or microbes or anything like that. That if we found them, look what we found on Mars. Oh no, they came from Earth. False positives were things we were very concerned about. And so basically, we had then each oven had a set of little trap doors that opened like French doors, just basically opened up, and so we would do one oven at a time. Well, we opened the first door, and one half of that French door did not open all the way. It was blocked some way, and we didn't know why. And then, but it was open. The one side was open all the way, and it was open, about a 60-degree angle or something like that. Right underneath those doors was a fine screen, about 1 millimeter holes in this screen, because we didn't want larger pieces of material to go in there and block any of the mechanisms in it. The ovens were very, very tiny. They had an opening of only about 1 millimeter across or something like that. And the idea was, so we had a very small oven because we had to have lots of insulation and not all that much power, and we wanted to get up to 1,000 degrees Celsius in temperature, so it had to be very efficient. Well, anyway, so they dug up a scoop of dirt or Martian surface material from, and we decided, I've forgotten who actually came up with this bright idea, but in order to identify different spots where we were digging, we had to have some kind of a naming plan. And so they came up with fairy tale characters as naming the different areas. And so the first sample we took was Baby Bear, and it came from the Goldilocks area. Mm-hmm. Well, I mean, this was fine. Made a little comic relief during the day, too. But anyway, so Baby Bear was the first sample that we dug up, and we're going to cook Baby Bear. Well, thing is that we didn't know how much material we were going to get. The scoop was about 2.5 inches wide and maybe 4 or 5 inches long, something like that. And it was on an arm, and it was basically like the human arm. There was a shoulder that mounted on the spacecraft, then there was an elbow halfway out, about a meter out, and then another meter, the lower part of the arm, and then a wrist joint that could move a scoop there was like a hand. So it was basically modeled after a human arm and hand. So anyway, it would dig like a backhoe, would dig up a sample. So we got this sample, the surf, and it was fairly loose material, could dig very nicely. And they dumped it on the first oven, and it was way, way, way too much material. And it stuck there. Now, we had that screen there, but if you put flour in a sifter, the flour is never going to go through the sifter until you shake it, because it's kind of adhesive. The material is quite adhesive, but this material from the surface of Mars was just like that. None of it went through the screen. And so we had a mechanism built in as a little vibrator motor. So we could vibrate the screen and vibrate the funnel under the screen that would lead anything that came through the screen down into the oven itself. And nothing happened. There was a little laser detector underneath there that would detect how many particles came through and, whether or not the oven was full. Nothing came through. We did this on 6 successive sols. And of course, there's a limited amount of time that we could shake about half an hour each day, and nothing came through. Just very sticky stuff. And so on the 6th sol, we were just about ready to give up, and lo and behold, it just flopped right through and filled our oven, and everybody cheered. And so we cooked it. No water, 0 water. So the scenario is that what we figured out is that probably what happened is that when the spacecraft landed, there were 6 retro rockets that were hydrazine rockets, which slowed the spacecraft down. But of course, there were hot fumes coming out from the rocket exhaust that was pointing straight downward. And it did blow some of the loose dirt from the surface away from under the spacecraft, and actually uncovered an area that's probably about a foot in diameter or something like that, which was bright white. And we called it the white stuff. We didn't know what it was. It probably was ice, but it could have been salt. Salt is white. And so, there could have been several things. So it was called the white stuff. It turns out it was water ice. We think what happened is that some of that surface ice actually melted due to the high temperature of these rocket fumes, exhaust coming out, and sprayed this area with a coating of water. There were also some pieces that flew up and landed on the surface of the deck of the spacecraft itself. And when we did our first atmospheric measurements with the instrument, we got way too much water vapor over what was expected to be in the atmosphere. So we think we were measuring the water that came directly from. Now, that wasn't a sufficiently firm analysis that we could say, we've identified water. That was, it was another thing that we did, but it wasn't the final definitive analysis. So we think what happened then, the sublimation rate of this ice on the surface of Mars was very high. That means sublimation is the process of changing from a solid to a liquid, solid to a gas without going through the liquid state. And that rate was very high. See, it's too cold for liquid water to exist on the surface of Mars right now, because the temperatures were, 20, 30 below zero, something like that, on the surface in the daytime. And so what happened then was that material that was sitting on that screen on top of the oven was sublimating all the water out of it. And it just took 6 sols before it all got out, and then the material that was left was very nice, loose, powdery stuff, and it went right through the screen and into our oven, but the water was gone. Later on, when we moved to a different area, we moved to a Snow White area, just named that, and we're able to dig. We find a different type of material. In both cases, when we dug down about 5 centimeters or 2 inches, we actually hit a hard surface. There was loose material above that, and we dug down and about 5 centimeters down, and that's exactly where the original analysis of that data from an orbiter from the Odyssey instruments, the analysis that Bill Boynton did said that we should find the ice 5 centimeters below the surface. And exactly that's where we found it. And so in this other area, we found that the soil was much harder than at the Baby Bear or Goldilocks site. And the people that built the arm and the scoop and all that, they realized that we might run into some very hard materials, that the scoop didn't have enough strength. I mean, when you're out there for 2 meters out there, you don't have a lot of digging strength on a very lightweight arm. It's not like a backhoe here on Earth. And so they had built a little rasp on the back on the heel of the scoop, that they had a little vibrator there, and they could actually drill a hole. And so they drilled 16 holes in the surface there, and were able to scoop up the materials that came out of these little holes. They're probably an inch deep or something like that. And that's what we finally got, that material scooped up and got it into an oven later on. And that's the one where and there was some dirt with it, of course, and that's the one where we actually cooked it and found that there was water in it.
We're visiting with space scientist John Hoffman from the William B. Hansen Center for Space Sciences at the University of Texas at Dallas. So the sample that you took ultimately confirmed the presence of water was from Snow White? The
Right.
Snow White sample area?
The sample that we took out of it, the name of the sample was Wicked Witch.
Wicked Witch from Snow White confirms presence of... Wow.
Right.
Take me through what went through your mind at the moment of actual confirmation. Where were you? When did it happen? And what were some of the thoughts that went through your mind?
Well, of course, we had different areas in a very large room in the what's called the SOC, the Spacecraft Operations Center, which was a building that the University of Arizona had purchased and refurbished exactly to be the headquarters for this mission. And when we found the water peak in the mass spectrum, and they found the actual when the temperature rose up to about 0 degrees Celsius, which is a melting point of ice, then it took a lot of extra power input, which was measured very, very accurately into the ovens, in order to actually melt the ice before the temperature would rise again, because that's the way it works. So you have to melt all of the ice before the temperature of the oven is going to be allowed to rise, because all the energy you're putting in is going to actually changing the state of the material. And so we saw that, and then we saw that the water vapor peak, and then so we said, we got it. And of course, when we announced it, everybody cheered. But then we realized that we had accomplished that part of the mission, which actually, to the scientists involved, wasn't the prime thing that we were interested more in mineralogy and what else was going on. But that was one of the goals that was set up by NASA headquarters for this Phoenix mission. And so, of course, we had to satisfy that goal and satisfy all the people at NASA headquarters, which we did. And then we were then freed from that particular goal, so we could start doing other things.
On to the next project.
On to the next part that we wanted to do, right.
I mean, for most of us in the lay community who don't do space science research as you do, I think this has been, and maybe even for the space community as well, truly one of the great scientific questions of the last century or so. And so I just wonder about your thoughts moving ahead in your own research and career, knowing that you've been a part of this. Well, something to brag about among your colleagues?
Oh, yeah, certainly. But, I've been through, this is not my first mission. Mm-hmm. I started out with the moon, well, of course, Earth orbiting satellites, and everything you discover is exciting along the way. And of course, getting to the surface of the moon and looking at the gases that were in the lunar atmosphere, and then going to Venus and finding, particularly in the Venus situation, we found that the argon isotope ratio was 100 times different than on Earth. Totally unexpected finding as far as Venus. And that was quite exciting. And then, of course, flying past Halley's Comet, that mission was run by the European Space Agency, so I was over in Darmstadt, Germany during that flyby, and that was kind of exciting. And we were watching, things on again, you always have a computer terminal and you can watch things, but you have headphones in that case, and you can hear the whole mission, everybody talking about it. And we were looking for dust coming out of the comet, because the comet is supposed to be a dirty snowball. It has a lot of dust that would be released as it sublimates the ice off the surface as it comes closer to the sun. And we weren't seeing anything. And the dust people were saying, is there a comet out there somewhere or not? And all of a sudden we hit a wall of dust and almost ruined the whole spacecraft. And we just it was about 600 maybe close to 1,000 kilometers away from the comet itself. And we ran into this big wall of dust particles. And so there it was. Everything like that is exciting. And But and the Mars was certainly equally exciting, if not more so.
Of all of your many instruments in space that have performed research over the years, missions of discovery, your time at the Naval Research Lab in D.C., and over the years teaching countless students as this organization evolved into a full-fledged 4-year plus graduate education institution. What are you most proud of accomplishing?
We just talked about all the different missions, and of course there were other things than that, and Earth orbiting things, the ISIS spacecraft that ran for 10 years, the Atmospheric Explorer spacecraft, 3 of those that worked very well, and looking at the ionosphere of the Earth and all that. But then coupled with all that, or should say concurrent with all that, of course the university was developing. It was developing as a graduate school only for a while. Initially, my first years, when I was so involved with the Apollo missions and the ISIS and the Atmospheric Explorer and then the Venus mission, I basically bought myself off 100% and worked entirely on my research for the first years. And then I moved from there into getting into, the education part of the university. And so the whole thing was kind of going on, and I was, basically involved entirely in research for my first number of years here. And then, of course, I got involved in a little bit into the university administration. I was head of the physics department. I've been associate dean of the school, and taught a number of courses, and so I've seen the university develop. First of all as a graduate school, then as juniors and seniors only as an upper division school, and then finally in 1990 when we started to introduce freshmen and sophomores. And saw that program develop. Starting out for the first 3 years, we just had 100 freshmen each the first 3 years. And now, of course, we're up to, 1,300 freshmen, something like that we bring in each year. So, I guess I've had a little bit to do with the development of the undergraduate program because I've been, I was, associate dean for undergraduate education and, put in my 2 cents worth as far as policies and all that. And but these 2 things kind of developed, and they were 2 parts of my life, really. And both were very important and both were interesting.
Can you share your age, Dr. Hoffman?
My age? 79.
79. And as you begin to step back from some of your responsibilities here at UT Dallas, and you reflect on 43 years at an organization, I want to know what's next for John Hoffman. I want to know, what are you passionate about in terms of the next chapter of your life?
Well, I had been involved with music and physics all my life, basically, although there was a big hiatus from music there for a while. When I was in high school, I started playing clarinet, and I, kind of carried that on through college. And then I just had a big fight with myself, as I imagine most people do. What am I going to do for my life? And it was a question about whether it be science or music. And my dad was, of course, science. He was a chemist. He was head of the chemistry department. My mother was a very accomplished pianist and taught piano and organ and all that. And actually, we had aspirations for a while to being a concert pianist. She didn't quite go that route, but so we had music and science in the family, and grew up that way. And so when I got into going through college, and I decided to go into the physics instead of the music, and I went to, I was going to go to, on to graduate school. I figured that playing a clarinet, there were thousands of people who played a clarinet, and there would be no way to be able to do physics and be able to practice enough in order to, be able to play anywhere. So I switched to an oboe. And in those days, absolutely 0 people played oboe. Mm-hmm. And so I
way to stand out.
That's right. The way to do it,
mm-hmm.
because I probably wouldn't have to be quite as proficient on the oboe as I would have to be on clarinet because mm-hmm. nobody played the oboe. So I started taking oboe lessons from one of the Minneapolis Symphony people. And I liked it. It was a great instrument. And, of course, you have to learn how to make your own reeds and all that kind of stuff. And so when I finally got up, I had been taking some lessons from one of the Minneapolis Symphony oboe players, and when I got to the university in the physics department, the first fall I was there, I got a call one day from the director of the University of Minnesota symphony orchestra saying, "Would you like to come and play oboe in the orchestra?" And I said, "Sure." They had no oboe players in the music school. And in those days, the university was 50,000 students. I think it's probably bigger than that now, but it was a big university. And they had 0 people who played oboe. So I got to play in anything I wanted to. And I had enough time to practice enough just to, keep up my proficiency. And so I played in the Minneapolis Civic Orchestra, not the symphony, but, the amateur orchestra. And we had a woodwind quintet, and it was great. And then I kind of, I got married and the kids came along and all that and working, I kind of dropped out of playing for a long, long time, for many, many years. And about 4 years ago, I picked up the clarinet again. And I thought it was easier to get back into it than the oboe. And I've been playing it ever since. And I play in 3 musical organizations right now. And as I pull back from the university, I'm going to go half-time in the fall. And I've resigned from being associate dean. And I'll be teaching some courses. And I'll probably develop more, my playing and just for fun.
Thank you so much for your time. It has truly been a pleasure, Dr. Hoffman. If it doesn't embarrass you, I want you to know that I and a lot of my colleagues share a sentiment that you are one of UT Dallas's treasures, and it is a real honor for me to be able to sit down with you, sir.
Well, thank you very much. I appreciate it.
This has been a conversation with Dr. John Hoffman, brought to you by the University of Texas at Dallas and the Office of Communications. To find out more about the university, our special guests, or 40 years of UT Dallas history, visit us on the web at utdallas.edu. UT Dallas, creating the future since 1969. Until the next conversation with, I'm Brandon Webb. Be well.